we are going to start talking about how to evaluate limits when we don't have a graph. Okay? Basically, when it comes to your test for Unit 1, which occurs on your gold sheet, it says the 10th and 11th. Okay? When your test occurs on the 10th and 11th, you're going to be asked to evaluate limits using a graph and analytically, which is without a graph, use logic and algebra. Okay? So, we're going to talk about some rules today. We'll start off with very simple one. Okay? Here's the deal. Don't start writing it. Just look up here. There are some things that we write down, like prefacing something. I don't feel like you need to write all of that in your notes all the time. So, my advice to you would be to write basic limits and write down these 3 things right here. This is how it looks in your book, but I don't think you need to write down everything else. Okay? So write down basic limits, write down those 3, and then we'll talk. Let's talk about why we have these rules. B. B is a number. B is actually a function. So if we have f of x equals a number, what does that graph look like? What kind of line, Eli? Okay. This is what we have going on. No matter what limit I ask you about, what is the y value approaching? We're going to say if this is y equals b. Sorry, I didn't set you up very well to answer my question. If that's y equals b, the y value is always b. Okay? So anytime you have a limit and you have just a constant right there, hey, you don't have to do any work. It's just that constant. Okay? That's what that's saying. Y equals x. Okay. No matter what limit we're talking about, the y value is going to be the same as the x value, right? All of these coordinates are x, y, x, y, x, y, 1, 1, 2, 2, 3, whatever. So whatever this value is that we're approaching, well, the y value is the same thing. Okay? So if I ask you for the limit towards 1, the y value is 1. If I ask you for the limit as x approaches -2, the y value is -2. And then that's going to be true for any polynomial. Essentially what I'm asking you for is the y value, right? As long as we don't have any like holes or asymptotes, okay, we can take this number right here and plug it into our function to figure out what the y value is, okay? So when I'm asking you for a limit, I'm asking you for the y value that we're approaching. As long as there's no holes, we have nothing to worry about. We can just plug that number in. So, if I ask you, I don't know where my page extend is. Ah, there it is. Okay? If I ask you for the limit as x approaches 2 of 5, ooh, I hear 2, I hear 5. Is it okay to be wrong?
Yeah.
It's okay to be wrong. Okay? It's that number that the y value is, okay? So 5 would be that limit. Thank you for being brave. Or was that not you?
Yeah, no, it was.
Oh, okay. The limit as x approaches 2 of x. When I plug 2 in for x, we get 2. Aren't these nice, right? Yeah? Can you handle this? The limit as x approaches 2 of x cubed. What's the y value at x cubed when x is 2? 8. That's our limit. We drive our car on that polynomial, we're going to approach 8. Okay? I can give you those all day, right? Okay, I'm going to come back to these. Don't worry about those. Okay? Essentially what we're doing is we're
Autumn, safety.
It's my fault for trying to. Okay? Essentially what we're doing is called direct substitution. As long as we have a graph that doesn't have any breaks in it, we can simply plug the x value in to the function to figure out what the y value is, and then we can determine what our limit is. Okay? What we have to worry about is if we have a denominator and we plug in a number and get 0. That's going to be our first warning sign. If we get a 0 in the denominator, then we either have a hole or an asymptote, and that's like a red flag for us. Okay? So as long as you can plug in values and you don't get a 0 in the denominator, then you can direct substitution. Plug x in for the function. Boom, there's your limit. Okay. Now, when you go look up in your book, there's going to be all these rules, okay? I feel like when I say direct substitution, okay, it's going to apply to a bunch of different kinds of functions, okay? Direct substitution means we take x, we throw it into the function, there's our limit, okay? As long as we have a polynomial, it's going to work every time. So your book has this rule about if it's polynomial, then we can plug this value into our function, and that's our limit. So if I were you, I would write polynomial, and then I would copy that down right there. Okay, as long as it's polynomial, we're going to have direct substitution work every time. Where we need to be careful is when we have a rational function, we can use direct substitution, but this guy can't be 0. Okay, you can plug in directly. You can plug in directly to get our y value as long as we don't have an asymptote or a hole there. I'm going to take you through a few examples, okay, and talk about some of the other types of functions that we are going to encounter. But I want to come back to that page that I skipped briefly. Don't write it down, okay? I don't think you need to write it down. It's in your book if you really feel that you need to reference it. But there are some things that we talk about in math that I feel like you all might assume anyway without me having to tell you. And what I have on that slide that I skipped that I'm going to go back to are some rules that I think are fairly intuitive. Okay? So don't write these down. I clicked the wrong way. Don't write these down. But basically what it's saying is if you have like addition or subtraction inside of your limit, you can take the limit of f and you can take the limit of g and you can add them together. I think you would have assumed that anyway. Okay? If you have two functions being multiplied inside of your limit, you can find the limit of f, you can find the limit of g, and then you can multiply those together for your answer. Okay? A lot of us aren't even going to think of that rule. We're just going to plug things in and go for it. Okay? So if you want to look at these, you may. But I feel like there are going to be things that we're just going to do automatically anyway because we're so routine in doing these operations with our functions. So, 2 examples, write them down. And I might do that for you. We have a polynomial. Anytime you see a polynomial, you should like do a little happy dance inside. Okay? All we have to do is substitute. 3x plus x squared. Our limit is 18. Okay. For this second limit down here, is that x value going to make the denominator 0? No. It is not. This is Miss Holman. Hi. I do. Yes, when we finish notes, I will send him down. All right. Eli, when we're done, Miss Williams in the athletic office needs you to pick something up. Okay? All right. So we have 2 over 27. Okay. How are we feeling? Feeling good? This is nice. Okay. One more type of function that we don't have to worry about is when we have a radical. Okay, so don't write this mumbo jumbo. Just write that. Okay. If we have a radical, as long as we have an x value that belongs in the domain of the function, we can use direct substitution. Okay? The problem would occur is if I asked you for the limit as x approaches -2 of like radical x. You can't do that. It doesn't belong in the domain. Okay? I won't do that to you. But as long as that c value is in the domain of our radical function, we're good to go. Okay? So we have that example right there that you can write down. I like 3s today, apparently. All my examples have involved lots of 3s. Okay? Since it's a radical, we don't have to think twice. We can just directly substitute. Guess what, guys? You will not get counted off if you leave this as radical 27. Welcome to AP Calculus. If you don't reduce, I'm not going to throw a fit about it. That is the least of my concerns. The AP test does not count off if you don't reduce. So if you leave this as radical 27, I am not going to dock you points. If it bothers you and you make it through radical free, awesome. Okay? Either way is fine. Okay, now, you all have been feeling like, man, this is like the best math class I've ever been in. Nothing we've done today has been overly strenuous. Let's go back to that case where I said, as long as the denominator is not 0, you can use direct substitution. Did anybody think what happens if it's 0? Okay. So, sometimes we're going to have to use some algebra, and I'll tell you when. So, go ahead and write down this example. Okay? But the rational function limits, that's where we need to be very careful. Because we can either have a whole or an asymptote. Now, if there's a whole, we might be able to find that limit. But if there's an asymptote, we cannot find that limit. We have unbounded behavior. Okay? So, let's just think for a minute. If this is really small, let me make that bigger very quickly. Okay. If we were to use direct substitution, what would we get? And I don't even, there should not be an equal sign right there. Erase that in your notes. That happened to my notes yesterday too, didn't it? These computers. Okay. So it's really strange. We had PCs last year, Macs this year. Some of the formatting gets all wonky when we switch from one to the other. So, if we directly substitute 2, what's in our numerator? What do we get? In our denominator. Okay. We can use algebra and maybe simplify this and see if we can get a limit to work. So I'll tell you right now, if you get 0 over 0, there is some algebra that you can do. All right? So I picked a nice example for us. Our numerator can factor to what? X plus 2, x minus 2. Okay. Well, what happens? These factors cancel, which, think back to what we talked about yesterday. What's happening graphically there? We have a whole. So now we have the limit as x approaches 2 of x plus 2. Can we now use direct substitution? What's our limit? Our limit is 4. Okay? So just because we get a 0 in the denominator doesn't mean we have to stop. If you get 0 over 0, there is some algebra that you're going to be able to do. Go ahead, and in this case, we could factor and cross out. I'll remind you what this graph looks like. Since we canceled out x equals, or x minus 2 at x equals 2, that means we have a whole. And it just happens to be at y is 4, which is why we got that to be our limit. Okay, that limit does exist. All right, let's look at another one. Oh, geez. And I have to go back and fix all of these. When we use direct substitution, what do we get in the numerator? What do we get in the denominator? I'm so sad. Okay, but that's a good sign. Maybe we can do some algebra. What algebra are we going to do, Mrs. Holman? We can't factor. 10 seconds. Talk to your neighbor. Who thinks they have an idea? Who think?
Multiply top bottom by radical x plus 1 plus 1.
What's that called, Nick?
I don't know.
The conjugate. Okay, if we multiply by a conjugate that involves a radical, the radical will disappear, right? Because of that a times a plus b times a minus b is the a squared minus b squared. Okay, let me write that. I just said something really fast. Please remember that when we multiply conjugates and when we FOIL, the o and the I end up canceling out, we get a squared minus b squared, right? So if we multiply by conjugates that involve radicals, those radicals will disappear. So, great suggestion, Nick. What we have is the limit as x approaches 0 of a squared minus b squared So in the numerator, what do we have? We have an x. Ooh, in the denominator, we have an x, right? So we can simplify this down to 1 over radical x plus 1 plus 1. And now we can use direct substitution. Do I need to go through that simplifying again?
Yes. Yeah.
What's 1 minus 1? Okay. X is canceled. Now we can plug in 0 to get 1/2. Future question answer?
Yep.
Okay. So we're okay with that conjugate. Eli loves it. I heard it.
Yeah.
I heard you say it. Okay. Those are the two types of problems you're going to see that involve rationals, okay? One where you have to factor, this one where you have to reduce down, okay? Or multiply by the conjugate. Okay? When we talk about the limit of a composition, I'm going to go ahead and let you write this down. Okay? Give you a minute or two to write down the limit of a composition. Taking the limit of the composition is very similar to taking a composition. You do the inside first, and then you plug that into the outside. The rule would be good. I mean, at the very least, that guy right there. You might need what's leading up to it. You know what? Don't write that down. We're just going to go to the next page. Sorry. How many of you need a little bit more time to write down the definition? Okay. I feel like this class goes by so fast every day. Okay, so f of x is x squared plus 4. Write it down. F of x is x squared plus 4. G of x is radical x. I chose very simple. F of x is x squared plus 2. G of x is radical x. So if I ask you for the limit of a composition, I first want you to consider, just like we would any other time, what's the limit as x approaches 2 of the inside function? So what's the limit as x approaches 2 of radical x? Radical 2. So now we have the limit as x approaches radical 2 of f of x. Okay? So now we get to plug radical 2 in for f of x, which would give us 6. So we do the inside, then we use that for the outside. Okay, just like we would for evaluating. Okay. Now the last thing I want to talk about is something that sort of connects your quiz from Friday to here. Okay? What question is it? 1D, f of x plus h minus f of x all over h. That's what's called the difference quotient. Okay? And what we're going to do is we're going to actually take the limit of the difference quotient. Okay? Now, this is what your book has. Those delta x's. On our quiz, we used h. If you don't like the delta x, those of you in physics, help us out. It means, what's the delta? Change in x. If you don't like the delta x and it bothers you, write an h every time you see a delta x. When we were working on our, when we were like asking questions about our summer packet, I alluded to the fact to some of you, I think it was the whole class, if that h doesn't cancel in the denominator, you've done something wrong. Okay, still the case. All right. So if I give you a function, let's say our function is 2x plus 1. And I ask you to take the limit of the difference quotient. Okay. How many of you it truly bothers you the delta x? Okay. How many of you really don't care? Okay. Just to be consistent for what we did on our summer packet, I'm going to just replace all the delta x's with h. Just please know it means the same thing. Okay? So we're just going to do h's here, just to make our lives a little bit less stressed. So f of x plus h minus f of x all over h. Do you notice how I'm subtracting that entire quantity? Some of you struggled with that on your summer quiz. Hint, 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 hint. Subtract the entire quantity. Basically, you need to reduce this down until that h in the denominator cancels, and then you'll be able to evaluate your limit. So we have 2x plus 2h plus 1 minus 2x minus 1. Because I distributed the 2 here. I distributed the negative here. 2x's cancel. 1's cancel. What's 2h divided by h? And the limit, as it doesn't matter, approaches 2 is 2. Okay? Your homework is super important tonight. Okay? You have to practice the limit of the difference quotient. You have to practice those rationals where 0 ends up in the denominator. Okay? If you have questions, come visit me after school. I'll be here.